Thank you. First of all, I want to thank Edgarson and his team for having me here. I'm really excited, and I want to thank you all for coming, guys. Uh, this is really a great opportunity to talk to other IT professionals because like we all are one big family, one big clan of IT people who will eventually rule the world because we own an information, we control it. But while we are getting there, I would like to talk a bit about the event-driven design. Before we start, I should mention a few things. I want to say thank you to all the team who worked on this presentation. I'm from Accenture, and we have a team there who worked on this presentation and on this topic overall. Specifically, I want to thank Mikhail Sagranats, who helped a lot with some theoretical researches. Uh, then I want to say that this is work in progress. We are polishing the stock all the time, and not everything is working right now. I will try my best to show you as much as I can today with the demo, but some parts unfortunately recently stopped working, and I didn't manage to fix them right before the talk. So I will probably in some places just explain how things gonna work. But in general, I hope I will be able to deliver the message. So don't judge me too much, and I will really appreciate your feedback and so on. So without further ado, let's go directly to event-driven design. So I hope you recognize the picture. It's a recent event, which actually happened on an Oscar ceremony when Will Smith hit other guy who is famous comedian for the bad joke about Will Smith's wife. Uh, I'm not judging this situation at all. I mean, it's not about judging the situation. It's not about saying that Will Smith's right to wrong. I mean, I personally against any violence. On the other hand, you cannot really insult whom others people love. But one way or another, this is a good example of what event is. Uh, so historically, there are different patterns and approaches in programming. And when it comes to distributed systems, event-driven design is one of the most natural approach. Why? Because we perceive the world uh, as events, as a series of events. Events is a very natural way for us to communicate to other world, and that's why when it comes to programming, is a very natural way for services to communicate between them. But before we will get there, let's first touch a question: what is event itself? So event is basically a signal which shows that something has happened, and of course something relevant to our system. What's important to mention here that event usually immutable because event again shows that something happened. It's already happened, and there is no need to to change. I mean, it's not even not need. There is no possibility to change it. It's already past. It's already a fact. That's why events usually immutable and they never change. Uh, Usually, one events lead to generation of another events because events bring information to the system. System processes this information and generates new events and so forth and so forth. And with such cascades of events, we have something which you can call history, basically. And that's one of the huge benefits of events. So events is a different way to represent system state in comparison to, let's say, uh, general database. Why I'm saying database, I will get here in a moment. So when we want to represent a system state, it needs to be recorded somewhere. It can be done in memory, it can be done on a hard drive or by other means. But generally, we can say that this collection of data can be called as a system snapshot, something which represents the state in which system is now. In contrast to that, events, each individual event does not represent the state of the system as of now, or at least not only represent that. Events are usually timely ordered because they happen in time, and each event normally has a timestamp which shows when exactly it happened. And if you put all these events together in one big queue, what you will get is something called an event log. And this event log is actually something which we can call a history of the system, history of the system state. Basically, with this event log, we cannot normally say what is the current system state, but what we can do, we can rewind system in past, system state in past. We can fast forward then system state in future, and this gives us a lot of opportunities in contrast again to current system state. Benefits, again, it's not a silver bullet, and not always it's a benefit. For instance, one of the benefits of, let me see, one of the benefits of using let's say, flat system state is an ability to query it in the same way like you query a database with some complex queries and get information relatively fast. With event log, you usually won't be able to do it, because with event log, in order to get system state, you will have to basically process all events from the beginning of the log to the moment on which you're interested in, or to the current moment if you're interested in the current moment. So this takes considerably more time. But for instance, if during your system lifetime somewhere there was a mistake, event log gives you an opportunity to go back, do the change or remove erroneous event, and then replay events after it to get the system to a normal state. And this is a huge advantage because this gives you a time travel feature in a sense. Events, what is mentioned here, that usually when you build a system, when you build a distributed system, events should not be, so to say, closely coupled to existing services, because of nature of events that they are stored and can be replayed. Events are very effective when it comes to introducing additional services. So you don't really need to change existing system. All you need is just to attach service to the event log, to the event broker, message broker. And again, a powerful feature, you can replay all events from the past through this new service to get it up to date, to get its state up to the current moment. For instance, if you have some upgrade to the system, this is a good way to test regression. Just replay all event logs through the new system and see if some regressions will come up, if state of the system will be as expected, and so on. There are certain problems when it comes to integrate between event-based systems and, let's say, I wouldn't call them legacy, but let's say not event-based systems, because I cannot say that they are obsolete, but on the other hand, there is a clear trend nowadays to use events. And this difficulty comes in the nature. Event communication is naturally asynchronous. And when you use events, we will talk about this quite a lot today. When you use events, you live in a sense, asynchronous world. It's totally different. It's again a contrast to the classical, let's say, microservice system where you have microservices which communicate via HTTP, via REST, and in this way you usually work in a synchronous way. That's why bring those two systems together. It's quite a hard task, and actually today we will be looking on it. One of the things I will be showing is how we transfer REST-based system to event-based system. What are the challenges and how we can solve them? Okay, there are some slides which are related to what we just discussed. I think we can skip them probably because we discussed majorly of all those stuff already. And let's talk about our demo or our example, which we want to show you. So as we were talking about movies, let's talk about example based on movies. Let's say we have some system which allows users to rent a movie, right? Such systems, there are quite a lot of them. For instance, Google Play, you can rent a movie you like and watch it, and then in 2-3 days you lose access, you cannot watch it anymore. Such system. So we have a customer service through which user orders some movie. Then we need to find if this movie exists. We have some basic search features like we can look for a movie by some shortened title. And also we can validate if user is eligible to watch the movie actually. And then we can do the payment for the movie rental. And if everything is fine, then we can watch the movie. So this is quite straightforward, right? There is a schema of business communication in the bottom. So there is a request for movie. We check if user is found. We check if movie is found. We check if user is eligible, and we check if payment is done. Let's say we want to switch to event-based, and let's see if we can win something. So imagine such a presentation of the system. What is changed here is that services communicate between themselves not with requests, but with events. Again, services do not tell each other what to do. We do not say, movie database, fetch me this movie. What we do, we post an event in which we say, this movie was ordered. This is a fact. Movie database sees that event, and basically it tries to find the movie, and if it manages, it responds that movie. And the same for payment service. It's events, communication is asynchronous. So basically, payment service and movie database communicate via Kafka, and they work in parallel. Obviously, if you have several services which have some complicated operations, then this greatly improve performance and also give you some flexibility. For instance, one service doesn't need to know about another, so Kafka serves as a like universal proxy between them. And as long as your events are designed, let's say, with some extensibility in mind, you can easily add or remove services without impacting the whole system, which is usually not true when it comes to REST, because you will have to change APIs. You will each service has to know about other service, at least those services who talk to each other. In our case, all this is not true. Also, some additional benefits. The event logs are quite often durable, which means they preserve and persist events, which gives us another advantage, especially if we are using cloud provision services. Like, for instance, if we are using Kafka as a provision service on Amazon or other cloud. In this case, we are also getting persistence, well, not for free, but we are getting persistence out of the box. As soon as your event is submitted to the message broker, at this moment, you can count your event as persisted, and you use fire and forget principles. However, there are complexities as well. If you will look on the business flow at the bottom, you can notice, I haven't said it on previous slide. Obviously, green lines are a successful pass, and red lines or orange lines are a failed pass. So, do you see a problem here? Let me put it this way. I will give you 5 seconds to think. So let's imagine that by some reason movie is found and payment is done, but then user is deemed not eligible. In this particular case, it's a problem because payment is already done and we basically need to undo the payment. And the first solution you would think of will be a transaction, obviously. Well, here is a complexity. So when we talk about events, sorry, let's get back for a moment. When we talk about events and when we talk about transactions, problem is that we have multiple services participating. Often we have multiple databases participating if we follow pattern one database per microservice. And in this case, we have to use something which is called distributed transaction. And how exactly distributed transaction works and how exactly we can utilize this distributed transaction, we actually gonna talk now. One question, Edgar, probably to me, how much time do I have? Edgar, are you here?
Yes, you have approximately till 7 plus Q&A.
Okay, I'm just thinking, should I go with transactions first and then with demo, or should I do demo now? Okay, let's first finish with our discussion, and then let's take a look on the demo. Okay, so one way to do a transaction is a distributed transaction is use so-called two-phase commit. I don't know if you have encountered it. I once did in my practice, and I should say two-phase commit is an ugly creature. Two-phase commit is a situation when, in order to do transaction, you on a phase one check transaction possibility without actually doing transaction, and then after every participant of the transaction, like participant 1, 2, 3, 4, actually confirm to you that transaction can be done. Then you implement actual transaction, as you can see. So there are two phases. It looks like it's a good solution, and theoretically it would be, but there is one big problem why I'm saying it's an ugly thing, because it doesn't work properly. Let's put it this way. I mean, there are implementations of two-phase commit. There are implementations of distributed transaction pattern, but unfortunately, usually they are very complex, and there is always problems with concurrency, problems with transaction isolation levels, problems with performance, with delays, and so on and so on, with order of transactions, order of commits. Sometimes it's important. And this is one big problem of two-phase commit protocol. It's slow and complex by design. And this really leads to performance degradation and all sorts of weird bugs, which are really hard to fix because often, well, they are not bugs in your code, but some corner cases which library doesn't cover, library you use. Another problem, maybe less important, but still worth mentioning, that two-phase commit is actually not supported by NoSQL databases. And currently, in many projects, in many cases, NoSQL databases are used in order to make sure that in order to make sure that you get a good performance, especially when data you store is not complex, it does not require complex relational database and schema and so on. Of course, two-phase commit doesn't help us in this situation. So is there another way to fix this situation? Is there a way to overcome challenges of two-phase commit, especially in the event design world? Well, yes, it is, and it is called Saga. I don't know if you have heard of this pattern. It's again quite popular nowadays. Saga basically allows you to do transactions without blocking them. So, in contrary to two-phase commit, which first kind of blocks all participants and waits until they will confirm that they are ready to do transaction, and only then undertakes transaction. Saga does transactions step by step. So whenever each participant requests a transaction request, it can do transaction. However, if by some reason one of the transactions will fail, what Saga does, it does reverse transactions. Reverse transactions which basically undo the changes done by transaction, by local transaction. This gives, well, this removes a lot of complexity, because instead of dealing with one huge transaction on many services in parallel, you are basically dealing with a sequence of simple and classical transactions. On the other hand, it creates a problem of having those reverse transactions. First of all, not always it's possible. Secondly, even if it's possible, there are certain requirements to those transactions. For instance, idempotency. Those transactions are normally should be such that they allow you to cancel changes, and the problem here is what will happen if you do changes and someone does changes on top of your changes. In this case, idempotency works in a way that when you do this transaction once and remove your changes, another subsequent reverse transaction will not break your data. And this can happen in case several transactions will break. So this transaction will break, this transaction will break. Again, they are not necessarily sequential, they can be parallel. And in this case, you can get several reverse transactions at the same time. That's why idempotency is important. Last thing I want to say about Saga is that generally there are two ways to implement it. One way to implement Saga is a choreographical way. Well, what does it mean? It means that each participant of Saga transaction actually responsible for this reverse commits and reverse rollbacks in initiation. As soon as any transaction will fail, it will request rollbacks on itself and on all other participants. This works quite well in case you have just one transaction, but as we discussed on previous slide, as soon as you have several transactions, you may be in trouble. Another disadvantage of, another advantage of such approach is actually that you don't have single point of failure. So even if by some reason a service which initiated transaction will fail and will not be available anymore, transaction will still be able to handle itself and either commit or rollback. But again, it's quite technically complex, and also it requires, for instance, visibility between all transaction participants. So each transaction participant should be able to reach out to other transaction participants, which is not always desirable. Orchestration, on the other hand, is something different. The difference, key difference, is in that when you do orchestration, you have a single transaction orchestrator, Saga orchestrator, a single service, usually initiator of transaction, which actually handles rollbacks. And as soon as some transaction will fail, it just notifies an orchestrator, and orchestration happens, and in centralized way, rollbacks are sent. This is simpler to implement. This is actually something we try to implement within our demo. Unfortunately, it got broken recently, and I won't be able to show it fully working today. But this approach is technically simpler and allows you to get the same transactionality, but unfortunately with a single point of failure. Okay, that's all slides I have, and now I want to spend a few minutes on a demo, if you don't mind. So again, let me remind you how our system looks like. It's a customer service, movie database, and payment service, and they are connected to one another with a simple REST, and we would want to get to this. So we want to transform this classical microservice-based system to this event-based microservice-based system. I actually tried to do it with a minimum usage of external libraries, just in order to show you how this works under the hood, what challenges you encounter and how they can be solved. So there won't be any fancy libraries and black magic annotations or something like this, which solves everything with one click. I did use Spring Boot. I accept that, but only to remove boilerplate code. So there is no black magic when it comes to transactions and communication and synchronicity and such stuff. So let's take a look on initial design. I don't know. I will be switching probably to. I don't know if it's a good idea because I will need to jump between classes, and I'm not sure it's really convenient. So maybe I will try to show it in this way. Please tell me if you have troubles seeing the code. Okay. Okay, let's start then. Let me see. So this is the classical version. I will, but just want based on Spring Boot, so nothing interesting for those who work with those services with the Spring Boot. Sorry. So customer service takes a request from customer and then calls sequentially all three services. First, it gets user from some local repository, which is represented by very simple class, which just returns some user from the predefined list. Then, sorry. Then it takes user, then it requests movie, check if movie is appropriate for the user, checked on an age basis. So there are those ratings PG, PG-13, R, and they are hugely dependent on age. So it just checks user age against the movie rating, if movie is appropriate, and then it processes payment. Payment usually processes successfully and responds with a movie. So nothing uncommon here. I'm not going to stop here too much. So as you can see, we use simple REST template and call other services. Validation happens within this controller as well. I don't know what to show here. Nothing interesting here. Nothing interesting here. So simple domain classes. So this is very straightforward for you. Then if we touch movie database service, it's even simpler than that. Again, just gets request, searches a movie in its repository, either responds it or respond with a error code with the help of exception with error code. It's not an error code, but it's not content code, no content code, which is processed by customer service as the movie is not found. And payment service is also same way, simple and primitive. So nothing interesting so far, I believe. As you can see, it just processes payment also with a simple post call, and that's it. Okay, let's take a look. So this is representation of the system in this shape. Let's very quickly run it to see if it even works. And it was. Okay, let me run it. Okay, should be fine now. So if I will use a simple PI tester and I will request a movie Star Wars for June, I obviously will get it, right? So Star Wars rating PG, so available for everyone, all is fine. Let's say I will do the same for Nancy. Nancy is a young girl, I think she's 10 years old or something. All is fine as well, why not? Star Wars is a classic. But we also have in our library, I don't know, 50 Shades of Grey. Let's try to check through it. With a Nancy, this movie is not appropriate for her, so obviously she cannot get access to it. With a John, however, he's an adult, he's a father of Nancy, so why not? Okay, that was classical. That was classical design. I just wanted to show you how it happens. That there is some logging here and logging in movie database and so on. Now let me shut it down and let's try to convert it to actual events. event-based architecture. Well, first thing we will need for event-based architecture is obviously an event broker. Something which will actually deliver our events between services, and the good choice is Kafka. Again, I did very minimal setup, and I did very minimal. I tried to keep code as minimal as possible, so please don't kick me too hard for a lot of things like absence of error handling, absence of concurrency handling. That's done intentionally because I just want to show you the general idea and the key things to keep in mind. So let's bring up Kafka. Oh, yeah. And then let's say let's hope this will fly. Yeah, I believe now we will be able to see what we have. We have Kafka, it's absolutely empty, it works, and there is nothing inside. Okay, now let's start converting our service. So first thing we need to think of is that previously we had synchronous processing, right? Let me open it here as well. So here we had synchronous processing. Basically, we did steps one by one. But in case of events, we are not able to have synchronous processing. So the big question is, okay, how should we proceed then? Okay, up to here, we create a response object, we get a user, this is all synchronous. Sorry, no, not the right screen. Yeah. So first thing we do change. Sorry, that's just from some experiments I had. So first thing we change, as we discussed in this diagram, we move eligibility check to the end. Why? Because we want to win from performance improvements. If we will do eligibility check before payment, basically we will make payment service dependent from movie search service, which is not our desire. Our desire to make the system work as fast as possible. So we put eligibility as dependent service after movie service, movie search service. So we just move it from here to here. Nothing interesting here. Okay, but then we need to get moving. We need to do it asynchronously. There are several ways how to approach it, but probably one of the simplest is to use Java Completable Future class, which basically allows you to create some background task, create a new thread, do some work there, and afterwards either complete this future or complete it erroneously, complete exceptionally with exception. It's very similar to classical future. The main difference that there is a method, specific method complete, and specific method complete exceptionally, which actually allows you to transfer this future object between different methods and different classes, and this gives us advantage of asynchronicity. So if we will go to this get movie method, what we do here, we create a completable future, we do some job, and we respond with it. So in parallel with that, our method continues. The same happens with payment future. Then we check eligibility, and at that point we code movie future get, which will wait until we will get the movie or until we will get error that movie is not available. Then we do payment future get to make sure payment was completed, and then we respond with a movie. I should say that here is something what got broken. Unfortunately, Saga implementation is not working right now, so I took a bit earlier version. But that's exactly where Saga comes into play. To notice that, for instance, user is not eligible and roll back payment if it was already done. But unfortunately, I won't be able to show it now, as I said. Okay. What's also interesting here that you can go again. It's an earlier version. You can go with the same REST request as we did in previous version, but again in asynchronous way. It doesn't really give you anything. I mean, like you do it asynchronously, and basically you get asynchronicity, but you don't get event communication. So in order to get event communication, you need to configure Kafka. I will not go into details here, just to say that we have several topics, and we will subscribe for those topics, and we will listen to them, and each topic represents an event type. So if we will look into movie controller, we can see that what we do here, we send the request for movie to the Kafka, and then we are waiting either for receiving a message that movie was found or movie was not found. We introduced some ID which allows us to actually identify a specific transaction, and we keep those completable futures with this ID in a map. And what is happening whenever movie is found or not found, you basically with this ID identify your completable future and either completed or complete exceptionally.
Volodymyr,
Yes, yes.
could you make larger font or somehow make it easier visible for us?
Yeah, I probably can. As I'm talking on a single class, I can actually go to the presentation mode, but let me do it in another class because I want to just spend a few minutes on it as well, and I will be finishing. So this movie database controller, I wanted to show you that, okay. Where is it? Presentation mode, right. So with movie-based controller, again, the previous method looked like this. It was a classical REST implementation, right? So we were doing get movie, which, oh, it's written already. Okay. Kafka listener here actually listens for movie debate topic for request. As soon as it gets request, it processes it and responds either to movie found or movie not found topic. So this is just one way of implementing. This is one way of implementing. Of implementing asynchronicity and Kafka communication for classical application. Again, key points here that in order to go asynchronous, you should leverage things like completable future. And secondly, that when you do it, you should keep in mind transactionality, and you should handle this transactionality normally with a Saga pattern. I think that's it from my side for today. So, are there any questions? I know that there is some delay, so I will probably just stop sharing to see stream better.
You were okay. You were frozen, but now you're kind of back.
Yeah, yeah. So I can see some questions here in chat. So in this particular instance, would it be possible to replace the distributor transaction logic with a series of events? Yes, exactly. But the problem here that if we want to do it sequentially, it's not a problem. Okay, you can do it, but then the question is why you're doing that. What is the win? But the good thing with event that we can do it in parallel. We can basically introduce parallelism, and in this case, you will have to think about order of what is happening. And in our case, we need some kind of transaction, right? If we won't do transaction, what will happen? Basically, user can get several payments. So user is getting charged for the movie, and afterwards we know that movie is not eligible for him, or he is not eligible for movie, and that's it. So yes, you can do it with a series of events, but again, if you introduce event-driven architecture, you should ask yourself a question: why you're doing that? I hope this answers the question. Okay. Do we have some other questions? I think not. Okay, guys, so how should we proceed?
I think we can wait for like okay.
Mm.
Here's question. Here's next question.
Yeah, there is a question. Assume that completable future is just another thread for same is just another thread for microservice. How this will work with multiple instances of the same microservice? Not sure if I got your question correct. If we talk about several instances of the microservice, then we are talking about infrastructural layer. We are now going one layer deeper. We are now speaking about how we get concurrency and asynchronicity within a single service. If you talk about several services, this is more a load balance. But generally, uh, the approach will be similar. Just it should be implemented not inside the code, but more on a level of infrastructure. In general, a completable future is a way. It's a callback. It's a callback, but it's a controllable callback. It's a callback. Well, in JavaScript, for instance, you don't need such stuff because in JavaScript, well, you have ability to just take a function and transfer function somewhere. In Java, you cannot really do that, and completable future is one way to actually uh, control your background process, control your state in a sense. is the answers.
Let's wait for like a minute, one more minute, if there will appear some more questions. Meanwhile, I'm sharing here link to the Google form where people can leave feedback.
Yeah, your feedback is highly appreciated, guys. Thanks a lot. As I said, this is work in progress, and we're really looking for this feedback because we hope to get this talk to more mature level, and it's really great that you spend time today with us and listen to that.
Okay, so far I have got feedback from one person. I believe there is a place for improvement. We can get some more feedback. Uh, Meanwhile, while we are waiting for some more questions, if they will appear, I have it's present time, I think. So please remind me, what is the right answer? Dark chocolate or milk one?
To me, I mean,
Yes,
that one.
dark one. Okay. So since you have answered correctly, then here will be dark chocolate for me, and there will be also DevClub socks,
Oh, that's cool stuff.
and here will be uh, you know what's buff bandana, like this thing.
Yes, 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 yes.
Here will be Nine Brains, the gray one, and
Thank you, Edgar. I
Salman one.
didn't expect that, but that's really fun stuff.
So a lot of work need. So as you understand, our focus is that your feet are warm and your neck is warm. So
Yes, that's great. That's very important.
yes,
Thank you.
yeah, you are welcome. Thank you for presentation. Okay, we start to get some more feedback. Please
You can
give
share
a
them
thought.
with me later if
Yeah,
or
yeah.
is it just the votes like plus minus, or there are some comments as well.
There, people can give comments as well, and there is one comment right now. Would be interesting to hear some experience with Saga and event-driven architecture, since I challenged the statement about Saga even simplicity.
Well, Saga is not simple. Don't get me wrong. Distributed transaction is never simple. Let me put it this way. When we talk about distributed transaction as such, distributed transaction is complex because it tries to achieve isolation. So normally when you do transaction, you cannot see data changes until the whole transaction is completed. And that's a big problem of distributed transaction. With Saga, it does not achieve isolation. So it basically doesn't even try to do it. If you do those local commits, each local commit will change the data and this data will be visible. So you don't have isolation. But in many cases, this is not a problem. If you need isolation, uh, try to use pessimistic locking, for instance, and this can help you. Or try to avoid distributed transaction at all. I actually can, if you're interested, reach me out. We can talk about that. I have experience with that a bit because the best way to do distributed transaction is not to do distributed transaction. So to try to avoid it at all cost. And this is possible in many cases. Uh, Another thing also important about distributed transaction in Saga is basically order or race conditions. I saw number of implementation of distributed transactions for production level databases like Oracle DB. Uh, yeah, it was primarily Oracle DB. And in those cases, yes, it kind of works. But if you have several databases and several transactions participating, or database and message broker, you will not be able to tell who will complete transaction first. Will it be message broker who deliver message to you first, or will it be database which will commit data first? And sometimes this is a real problem because, well, simple example, you are transferring data from one database to another. you do distributed transaction when you write something in staging table, and in parallel you send a message for the service to pick this data up. If your service, if your commit in staging table will not be completed by the moment message will be delivered, service will find nothing. And I had such example in my practice. How we fixed it? Well, kind of fixed it. We introduced a delay between first and the second. But obviously, this is how to say rubber band solution. This is not how it intended to work. This is not how it should work properly. With this way, again, Saga with its reverse transactions doesn't suffer from such problems. Even if it doesn't matter the order, if something is not working, Saga can just roll back everything, and that's it. I hope this clarifies a bit.
Thank you for clarification. I think now it's kind of seems that there will be no more questions here. I still remind everybody, please give us feedback. If you can write some comment, you are very welcome. It will be very helpful for Volodymyr to understand what to talk about more or what to talk about less or what was not clear. So right now I'm saying thank you, Volodymyr. I will send you comments later.